Hello everyone. Today I will be presenting the science that goes behind Alexa's text-to-speech system and the work that we are currently doing at Amazon to make Alexa sound much more natural and engaging with AI. This presentation is going to be divided into 4 sections. The first is going to be around naturalness. The second is going to be around expressivity. The third will be around semantically aware systems. And the fourth is about always getting better, which is about contextual aware synthesis. So to get a brief understanding of text-to-speech systems, there are two axes on which they are measured against, which is naturalness and flexibility. And to give a brief background, before 2016, there used to be two kinds of approaches. The first one was a statistical parametric synthesis, which were really good on the flexibility axis, but they weren't as natural, meaning that they could give different kinds of prosody to the synthesized speech, but it still sounded quite robotic. And on the other hand, we had Unix selection, hybrid Unix selection systems, which had much more higher naturalness, that they sounded much more like humans, but they lacked on the flexibility. And with the success of deep learning technologies in text-to-speech domain, we have seen such models to kind of push up along this diagonal and be closer towards the human beings in terms of naturalness and flexibility. So to give a very rough understanding as to what goes behind a text-to-speech system, we can think of it as 3 subcomponents. The first component is the text analysis component, which takes in the text and produces the linguistic features. The second component is the prosodic generation component, which takes in the linguistic features and produces the prosodic features. And the third is the speech synthesis component, which takes in both the linguistic and prosodic features and produces the final acoustic signal. And over the years, all of these components have either been completely replaced or have been significantly improved upon by deep neural network technologies. And on one extreme, we also have end-to-end text-to-speech systems, wherein it is just one big model which takes the text as the input and gives the acoustic signal as the output. And even though there are some advantages to such models, the disadvantage is that it is very difficult to dissect these models and to understand why a model did something. So for practical and for production purposes, it is considered better to have these 3 subcomponents so that you can actually dive into any one of them and understand why a model did something and make changes if required. So let's dive a little bit into what are the different neural components within the text-to-speech system. And they are basically these 2 models on your left and on your right. So the first one is the prosodic generation neural model, which takes in the phonemes and the features as the input and generates a suitable intermediate representation, which is MEL spectrograms for this purpose. And the second neural model on your right is the universal neural vocoder in our case, which takes in the MEL spectrograms produced by the prosodic generation model and produces the final human-like sounding speech. So let's focus on the first neural model, which was the prosodic generation module. So this is a sequence-to-sequence model, which takes in the sequence of words as input and produces the MEL spectrograms. And it is an encoder-decoder mechanism wherein the encoder generates a suitable representation for the words that it has consumed as input. And that intermediate representation of words is fed into the decoder, while the decoder tries to iteratively predict the desired output, which is the MEL spectrograms. And in addition to encoder and decoder, we also have attention. And attention is something which enables the decoder to focus on certain parts of input during its output production. And over the years, attention has been recognized as one of the most critical components for the encoder-decoder models to work effectively. And going forward, we are going to take this architecture throughout in our talk. So let's first understand as to where exactly are we currently. So this is the concatenative system. Let's listen to it, how it sounds like.
Pike Place Market is a public market overlooking the Elliott Bay waterfront in Seattle. The market opened August 17, 1907, and is one of the oldest continuously operated public farmers markets in the United States. It is a place of business for many small farmers, craftspeople, and merchants.
And this is what the neural TTS model sounds like.
Pike Place Market is a public market overlooking the Elliott Bay waterfront in Seattle. The market opened August 17, 1907, and is one of the oldest continuously operated public farmers markets in the United States. It is a place of business for many small farmers, craftspeople, and merchants.
So neural TTS was able to give us much higher consistency and was quite smoother, but it sounded still quite like the concatenative system. So the next question is, can we add expressivity to neural TTS systems and gain even more flexibility out of them? So let's talk about the style information that we can get in a synthesized speech. So the architecture is quite similar to what we have seen before. The only addition to it is the speaking style information that we add to the attention mechanism. Now, we can choose recordings in a specific speaking style. In our case, we chose the newscaster one because it was quite different from the neutral recordings, and also because it was quite pacey. So we use recordings in both neutral and the newscaster style to train our systems. And we provide an additional label to all of these recordings to help the model differentiate between the neutral and the newscaster style. And once we have trained such a module, during inference, during synthesis, we pass this additional information of the speaking style along with the attention to enable the decoder to synthesize speech in that particular style. So let's listen what it sounds like. So this is the concatenative one.
San Francisco's $2.2 billion Grand Central Terminal open. Spanning 3 city blocks, San Francisco's $2 billion transit terminal is open after nearly a decade under construction. Coined the Grand Central of the West, the new Salesforce Transit Center near the heart of downtown is expected to accommodate 100,000 passengers each weekday and up to 45 million people a year. It welcomed its first passengers and visitors this month.
Now let's listen to the newscaster TTS style.
San Francisco's $2.2 billion Grand Central Terminal open. Spanning 3 city blocks, San Francisco's $2 billion transit terminal is open after nearly a decade under construction. Coined the Grand Central of the West, the new Salesforce Transit Center near the heart of downtown is expected to accommodate 100,000 passengers each weekday and up to 45 million people a year. It welcomed its first passengers and visitors this month.
So hopefully you could hear how both of these samples sounded really different. And the newscaster one was quite pacey as well. And it is representative of what a person might expect a newscaster to sound like. So now that we have styles, can we add emotions to it as well? And this is something that we try to achieve using disentanglement, wherein the neutral voice sounds like this.
I am playing a single hand in what looks like a losing game.
And if you move along the embedding space, you can get something like highly excited.
I'm playing a single hand in what looks like a losing game.
And if you go on the other extreme, you can also get highly disappointed.
I'm playing a single hand in what looks like a losing game.
Or you can get anything in between as well. So the important thing to note over here is that we have added styles and emotions to the synthesized speech without compromising on the naturalness of it. It still sounds like a human or near human-like. So now that we have covered naturalness and expressivity, let's move on to semantically aware synthesis. Now, this is more about the ability to interpret the text. So this system is also the architecture is quite similar to what we have seen before. And in addition to the attention, we actually add more language modeling information to the attention using natural language processing techniques. And this helps the decoder to understand as to which words or which phrases of the input should it give more weight on. And by that, it can understand as to which words and which phrases require what kind of emphasis. And this gives the listener the impression that the system actually understands what it is saying. And this is something which is quite important for what we call long form reading scenarios, wherein you have to synthesize longer passages of text like multiple paragraphs. So that is where it makes the most difference. So now let's move on to about how the system can always get better. This revolves around adapting the system according to where it is in the current dialogue or in the current discourse, according to the feelings, the intentions, and the emotions of the interlocutor. So this is something that we are still working on, and the architecture is quite similar to what we have seen before. The idea is that we should be able to rephrase a very generic Alexa response like, hey, to something more like, hi, what can I do for you? Which is more reflective of what Alexa skill intention is. And also to kind of incorporate what the user had said before and what the intention of the user was. And this gives the user the impression that the system is adapting to the conversation. And it is not just about the language, like it is not just about rephrasing the response. It is also about adding the suitable amount of expressivity to it. So for example, if you have to say something like, that's fantastic, you have to attach a suitable expression to the word fantastic to convey the right meaning, because we often convey our intentions with the way we speak and not just by the content of the text. So over here, we add more information to the model, which is like the Alexa application or the intention, to kind of drive that capability of the decoder as to what style and what degree of emphasis and what emotion should be given to the Alexa response. So let's listen to the neutral one over here.
Very happy to help. Let's find something you'll like on Amazon Music. How about something from the 80s? Does that work?
Whereas this is something which is more contextually aware.
Very happy to help. Let's find something you'll like on Amazon Music. How about something from the 80s? Living on a Prayer by Bon Jovi. Does that work?
So this is how the contextually aware systems work. And with this, we kind of end the overview that we have of the text-to-speech systems. And let's move a little bit towards as to what are the different teams that are based out of Gdansk offices. So one of them is the Alexa TTS team, of course, which is the text-to-speech team, and it owns the speech synthesis solutions across Amazon. The other is the Amazon Poly, which is a text-to-speech service owned by AWS, and it allows developers to create applications that talk and build entirely new categories of speech-enabled products. Within Alexa, we also have two more teams, which is the natural language understanding team, which builds and maintains cloud services that allow Alexa and AWS Lex to understand human language. And the other one is the Alexa hybrid engine team, which is a part of the larger Alexa speech team. And the objective of this team is to make Alexa available everywhere. And apart from these, we also have the Ring team, which belongs to the Ring Device Hardware Software Engineering Organization, and owns the development of products like doorbells, cameras, and other accessories. So I hope that this presentation was informative and exciting for you. Thank you for listening.